So, thanks so much for being here. A couple of housekeeping items. Please get your headsets on so that you can hear the speakers. And please, when we are done, your feedback is essential. Please rate in the app so that we know what's important to you and how we can make it better in the future. So without further ado, I'd like to introduce Henry Weller, Senior Product Manager here at MongoDB for Vector Search. And we're going to be talking about embedding the future. Thank you.
Thanks. I got it. Great. Can everybody hear me? Sweet. Well, thank you guys for coming to this session. I'm super excited to talk about the future, as was just alluded to. But before we talk about the future, I want to take a little look into the past. So it's been about 2 years since we've had Atlas Vector Search generally available. I've been the main product manager for it this whole time. And there's been definitely many lessons that we've learned from our customers, from building this type of system to support these sort of next generation workloads. And really in this talk, we'll talk a little bit about some of those learnings, but we're really going to project forward and talk about where we see things going and why we feel it's so important that to support next generation workloads, we need to have like a world-class vector search system that feels seamless to the database. Taking a big step back, maybe this is your first time ever learning about vector search. It's quite impressive if that's the case, but if it is, the basic idea is that you pass unstructured data through an embedding model, which is capable of representing a high-dimensional representation of it. So typically, high-dimensional floating point vectors, which can be compared to one another in semantic space. What was true 2 years ago is still true today. I would say the nature of the unstructured data has changed. More types of modalities are able to be embedded and searched against. We'll talk a little bit about that, but in general, how this looks in MongoDB is you might have a document where one of the fields is an embedded representation of another field. So here's like an earnings call, maybe a MongoDB earnings call, who knows, and you basically can see the source, you can see a bunch of metadata, and you can see an embedded representation of that source. You would then index this by creating a vector search index definition and query it. And we won't even talk about all that because it'll come up later on. What I think would be helpful is to understand, okay, this is the basics. This is actually kind of table stakes. What have you learned? Like this was what you put out 2 years ago. What is actually important as you look forward to the future for 26, 27, 28? I mean, you can only look so far ahead with the way in which sort of agentic application architectures are evolving, but there are certain things that are kind of common threads that we've learned. What it really revolves around is that there's this idea of next generation workloads, things that are very challenging to predict the interface of. A big difference between lexical search and vector search is lexical search, that search bar has not changed very much. You go to Amazon, you go to Google, you see pretty similar interfaces. Versus like a generative search experience, you might not exactly know what that ideal interface is or the right level of context to provide an LLM, but you do know that you need to be very adaptable. So it has to be very flexible, and you have to understand what those different workloads look like. That capability needs to be rock solid. It's one thing to have something that can serve queries. It's another thing to have something that's highly available, that's highly durable, that's secure, and that scales for hundreds of millions or billions of vectors, or thousands of queries per second. And then finally, this isn't the vector search.local, this is MongoDB.local, right? It would be a little bit missing the point if we put something out that had these capabilities, but didn't really feel like MongoDB. It felt like I was learning something else. So we'll talk a little bit about what that means to be seamless as well. Next generation workloads. I put a robot emoji because I think that is like people's first thought when they think of building vector search systems is working with AI. But we've learned that actually this looks like a lot of different things. We have tens of thousands of customers using the service at this point, and lots of different types of use cases have emerged. You have things that you might expect to see. A simple semantic search interface using a text embedding model, where embedded data can be compared to a natural language query. This is probably the most conventional way to use semantic search. It honestly kind of looks like lexical search to some extent if you squint, and maybe hybridize as well with hybrid search, as we'll talk about. and ultimately you're trying to get back a set of results. The step sibling of this would be RAG. So the most common application architecture for working with LLMs and databases would be doing something very similar, but instead of providing it to an interface and a human, you provided a set of results, typically a very limited set of results, to an LLM. This is sort of a jumping off point. I would say that we now have a lot more content around short-term memory, long-term memory, episodic memory, sort of other ways to be stateful for a large language model. But this is like a pretty general good starting point because it's sort of the prototype for everything else. One thing that people probably underappreciate is how often MongoDB is used as a metadata store for image repositories. And what we've learned from our customers is that vectors often can be thought of as metadata as well. So we see this quite a lot. Some of our largest query volume workloads look like image similarity search, look like identifying similar images to a query image or similar images to a natural language text using a clip-based embedding model or similar, or Voyage multimodal 3. Along similar lines, there's other modalities of data where vectors are really helpful. Anomaly detection, and I guess its cousin would sort of be recommendation systems. They're very similar. You're trying to find signals and commonalities or things that are out of band, things that are outliers. And vectors are very good at this. They're very good at identifying signals in transactions, in customer history, to understand, is this actually the person that I think it is that's doing this transaction or not? This is probably the biggest use case we see with a lot of the banks that we work with. And then this is kind of an interesting aside because it's not necessarily vector search, but it's sort of how people are building with MongoDB has changed a lot too because of LLMs. The MCP server that we have, which GA'd today, really is a really great way to make interacting with LLMs stateful to the context of your application. Meaning, don't just tell me how this query pattern works, tell me how to access the data that I have in this collection. And it will recommend to you the right aggregation stage, the right indexes, the right optimization path to sort of think about. I will caveat, it does not yet have full awareness of vector search and search indexes, but that will be added very soon. And once that happens, there will be, I think, a really nice tight feedback loop between working with LLMs and sort of discovering best practices when working with MongoDB and more advanced aggregation stages like search and vector search. I think there's a nice through line between all these different modalities of working with search and working with MongoDB that goes back to our roots as a company. MongoDB as a document database is really oriented around the idea of change. The idea that what your data model is on day 0 might not reflect what it will be in 2 years. And you might have an optimized data model that is very hard to evolve over time. The document model is fundamentally built for that kind of workload, but it's also in many ways built to present itself to new access patterns, maybe even for the same data set. So, and maybe even new development ways of working with the database, right? This has been fundamentally a game changer in how developers work, is that they work with coding assistants far more than they used to. 2 years ago, the LLM capabilities were nowhere near the capabilities they are now, and it's sort of table stakes to work with Cursor or Claude Code in many developer teams. So, we say change is good, and it's even better because MongoDB is built for change. Now, if we think about all these new workloads, it's kind of important to think about, well, what is this thing that you have? What is vector search, and actually how has this evolved to meet the needs of these workloads? Without getting too into the nitty-gritty, it's a different kind of index than what you have in your database. When you define a vector search index for fields X, Y, and Z, maybe several vector fields and several filter fields, you are using an HNSW graph. And this has been the case since we launched 2 years ago, and it's still the case today, but there's been quite a few advancements that really take this into sort of the next level of scale. The first is dedicated search nodes. So we've had this for a bit, and we've continued to add more ways to deploy your architecture for search separately, or deploy your hardware for search indexes separately from your database. The second is we've introduced a dedicated type for vectors. So we have a BSON type called bin data, and we added a subtype for vectors. Essentially, embedding models produce homogeneously typed vectors. We can use that and have a more compressed representation in the database. And then finally, vector quantization, which we'll talk about. For those that aren't aware of what search nodes is, maybe this is the first time you've ever heard of it. I have a coworker who says that it is resource isolation without data isolation. I think that's probably the best way to think about it. You still have the automatic change data capture between your database and your search index, but you're able to put them on separate hardware and scale them out independently. So high availability for search and scale up and down, independently from your core database. It also means things like resource contention between your database and your search index is not a thing. And if you have a memory resident index, like an unquantized vector index, that becomes a pretty big deal. We've seen with some of our customers that simply just turning on search nodes has dramatically improved the performance of their vector search workloads. This is, it's one of those things where it's like you want to work with software, you want it to scale simply. Dedicated search nodes is really the path for scaling your search architectures, and it shows up in terms of the performance that's experienced. Bin data vectors, just put simply, you take something that's human readable and you convert it into binary, which is like a third the size in the database. Mostly in the database, it's just a durability layer for the search index. So while it does decode in the Atlas UI to something that's human readable, it actually doesn't particularly matter if you need it to be human readable. And we have driver support for converting between formats. So if you pull things off the results and you actually want to work with your vectors, they're not just a means to an end, you can still do that. What I really want to talk about though is quantization. It's kind of been a big, I think, thing holding back vector indexes is the fact that they have to be memory resident. It's a property that is inherent to an unquantized index, but it doesn't have to be this way necessarily. If you look at the resource requirements for a model that was really popular a while ago, but probably I should update my slide, text embedding A2 is 6 kilobytes for 1536 dimension vectors. Doesn't sound like a lot, but if you scale up to hundreds of millions of vectors, this ends up looking pretty beefy, to the point where you look at the dedicated search node that it might go on to, and you're like, what the heck? Am I supposed to shard? But it just seems like I have to do a lot of things in order to support this, and that might be undesirable. So RAM resident indexes have downsides. Quantization is expressly intended to turn these indexes from RAM resident to disk resident by allowing you to work with reduced representations that are derived from the original representation. Without getting too into the math, what's essentially happening is you take each dimension of the vector across every vector in your data set, and you find the min and the max, and then you bin every single element, and you map it to a bin. So it could be 255 bins for an innate representation, or just 2 bins, 0 or 1, for a binary representation, as you see here. What's really powerful about this is you actually basically produce a derivative vector that captures a lot of the original information. And you can actually use the original vector as a secondary rescoring step, meaning build an index with the binary vector and then rescore with the full fidelity vector to kind of get back the accuracy you might lose. It sounds great in practice. A lot of customers, when they see this, they're like, there's no shot that a ones and zeros could work for my use case. I have massive amount of data, Henry. How is this possibly going to work? We've tested this. We tested this on a large data set with 15 million vectors and observed for binary quantization shown in the triangle and for scalar quantization shown with the square that for requesting 10 vectors or requesting 100 vectors, so on the left and the upper left and upper right, you can get very close to that 90 to 95% accuracy compared to an exact baseline. So I'm doing an exact search for a set of 50 queries to get the exact right results, the top 10 and the top 100. And how does my binary quantized search perform? Well, if I ramp up my query time parameter, I can get really darn close. Scalar, out of the box, is already quite close without needing significantly higher num candidates. But then you say, Henry, that's great, but 2048 dimensions is a lot. What happens if I reduce that? How does quantization interact with dimensionality? I would say that's a great question, and that is also something you can observe. Lower dimensions suffer more from quantization than higher dimensions do. At 1024 and above, these are all tested with Voyage 3 large. For those of you taking photos, I appreciate you. All this is in our docs as well. So just search Atlas Vector Search Benchmark, and this will be readily at your fingertips. The point is you can get 90 to 95%, not just at 2048. You can do it at 1024. You can even get close, if you look at the blue line, with 512. It's sort of like 85-ish%. It's topping out. And the latencies on the bottom are also not too bad. As you really scale up num candidates, you start to see the binary score, the binary quantization latency start to rip, and that's purely because of the rescoring. What's really nice about this is if once you've guardrailed against accuracy, you know you're not handicapping your search too much, you can change this from a RAM resident to a disk resident index, which dramatically changes the cost story. So we're going from I think it was the most expensive low CPU node to this S60 high CPU, which is a third the price. And since it's disk constrained, you can actually have extremely large disk search nodes that have just fewer CPUs, and you can continue to scale the amount of vectors you can index, again, before you shard. So yeah, it's 2 years in, and I still get people that are I thought MongoDB is good, but vector search, but only for 1 million vectors. Above that, I need to use a dedicated vector database. You're welcome to believe that, but I mean, if you look at the numbers, it's just not borne out by the reality of what the system is. In fact, we can go up to 400 million vectors with binary quantization using the same dimensionality I showed at the top before you need to shard. If you have a use case larger than that and you're trying to use our system, I'd probably know who you are. I've probably worked with you. But most people at this scale have had a very totally fine time with the system so far. What we've talked about is inherently has been this idea of this iron triangle of search. And what you're often told is you can pick two things. We've really been talking about speed and cost. We're really optimizing for that. And quality has been sort of a guardrail metric. What would be great is if we could talk a little bit further, right? We're working with vectors that have certain capabilities, but we would also really like to know that we're not just handicapping their quality to a safe degree. We would like to know that they're actually accurate in what they're doing. Put another way, it's kind of hard to have a very accurate search system if you don't have an embedding model that is very accurate, that you're very confident can represent your data in a strong manner. This is a large motivating factor for why we made this acquisition of Voyage AI. Voyage AI, for those that don't know, is a leading provider of embedding models and re-ranking models. So they provide domain-specific and general-purpose text embedding models. They also have a new contextualized text embedding model, which takes into account parent context. You can provide a chunking strategy along with a parent document, and it will split it for you and condition the child embeddings on the parent documents, or rather on the adjacent chunks. And then there's also re-ranker models. What's really interesting, and you'll notice that there's a consistent visual language between the benchmark plots we saw before and Voyages, is that for scalar and binary quantization, these models perform very well. In fact, on the data sets that they tested, I believe this is the Bear benchmark, they were able to outperform, in some cases, OpenAI's Ada 2 model with float vectors using lower dimension binary vectors, which is quite impressive. We're going to be spending a lot of time. I would say it's only been 6 months or so since the acquisition. You're going to see a lot more from us in terms of putting out new models, but also making Voyage integrate really nicely with Atlas Vector Search and with Atlas generally, which again is aligned with this idea of making this whole experience feel like a part of the database. But there's more. We have embeddings, but there's these other things that you guys provide, that we provide, which are including full text search. It would be a little crazy if we provided vector search and full text search and we never made it easy to have these things work well together. So really hybrid search, that experience is something that we've had consistent demand from our customers for having a solid sort of set of affordances around, and we'll be talking a lot about that now. Let's imagine that you are building an application that is a marketplace for subletting apartments. Now, you might have a document that represents an individual apartment, and it might look something like this. You might have the name of the apartment, you might have a description, you might have an embedded representation of that, geolocation, you might have reviews. There's lots of sources of information that are both sources of relevance, things that can be embedded, things that could be filtered on. But in general, there's just like a lot of rich information here. And you might actually be looking to combine methodologies rather than be locked into, oh, I'm just going to vector search the description and then that's it, or just do lexical search. So the idea behind hybrid search is really to account for the sort of large breadth of queries you might get and map them as much as you can to accurate results. Vector search is really good for open-ended queries. It's really good for what you might call low-intent queries. Like, I'm looking for a vibey Bushwick apartment. What is vibey? Maybe that's captured in the description. Versus, I'm looking for a Bushwick apartment. Like, it needs to be in Bushwick. Like, if it's around Bushwick in a radius of what that is, then that's somewhat relevant to me. Maybe that's a filter. But it's a totally different methodology of like a precise search versus a high intent precise search versus a low intent sort of vibes-based natural language open-ended search. What you would like to do is have both of these. So like the false negatives from one are captured by the other and vice versa, and be able to have a joint result set. We had a way of doing this. So fundamentally, the things we'll be talking about are actually compositions of existing features. The way that you could do this, though, was a little painful. You would do a vector search and a lexical search with a limit. You would pull out the rank using an unwind and produce a rank-derived score. You would combine these things using a union with, so maybe vector search union with $search, and then you would group on a common key, probably document ID, and then sum the weighted scores and sort on them. Really what you care about is like a very minimal set of things. Like you care about the search and the vector search and those subpipelines and how they're combined. A lot of the rest of this is boilerplate. And believe me when I say, even though it's possible, people will not do it if it's hard to do. They just won't. So that was really a motivating factor for Rank Fusion, which is rolling out to 8.0 over the next few weeks. It was supposed to be fully rolled out today, but it's coming in the next 2 weeks. This was first announced at 8.1. Which was 3 months ago, and it's available on 8.2 as well, which is out today. It's fundamentally going to be a way to combine ranked subpipelines. Meaning, I have pipeline 1, which might be my lexical search pipeline, and pipeline 2, my vector search pipeline, and I want to make combining these things very easy. I want to make, there's a default combination, which is just the weighted sum, and I need to provide the weights. I can combine in other ways, and I can also inspect the individual subpipeline scores if I ask for score details. So the syntax tree just collapses. You care about search and vector search, and you care about a couple of these boosting parameters, and maybe the arithmetic logic for combining, but that's it. That's it. Like, you don't need to do all this other unwind mumbo jumbo. What you might want to do is actually go a step further and say, hey, the rank is helpful, but I actually have a big gap between the scores in positions 1 and 2, and maybe a small gap between 2 and 3. If I only care about the rank and have a weight that applies across the whole methodology, I might lose that granularity. So score fusion is this thing that we have also announced today, which is very similar, but instead of operating over the rank, it operates over the score. And if you're working with a pipeline that doesn't have a score on it, we added another stage called $score, which can turn any field into a score, essentially. And you can use this to take the normalized scores, weigh them, and combine them to build, again, more accurate and simplified hybrid search experiences. All of this is really just trying to get at improving accuracy. There's a lot more that we'll talk about soon in terms of understanding when you're failing and when your results are not as accurate as they could be. But fundamentally, these primitives are available to you if you already have a good test bench for determining that. This sort of last section will be touching on what I call data actions within Atlas. This is not a trademark branded thing. This is just a generic concept I think is useful, which is there's a lot of things I would like to be able to do to my data at index time or at collection time, or whenever I insert it, that would just make things easier, so I don't have everything happen at query time. A simple example is indexing on views. You can create a view, and then you can build a search index against it. So this is an example that actually I use this to create that multi-dimensional benchmark I showed before. Instead of producing 5 million vectors of 4 dimensionalities, I produced 5 million of 1 dimensionality, and then I used a view which sliced the first n dimensions of that vector, and I created different fields within my vector index for each of those slices. In this case, it's just 2. For the example I showed before, it was 4. So if you're trying to assess dimensionality and you're trying to understand how accurate it is, something like this could be useful. But there's so many things you can do in a view that are now supported that you can build an index against. Very philosophically aligned with this idea of you want like a single source of truth, which might be your collection, and then you have views, which may be slight transformations of it that you can search against for different access patterns. Auto-embedding is another example of something like this. So let's say instead of needing to think about an embedding model and bring all of that to the collection and then embed your query, what if that was all done for you? So all you need to give it is a chunk data source and a user query natural language. This and hybrid search are probably the 2 most demanded features. Search and community, which we'll talk about shortly as well, 3rd demanded feature. What this looks like is a simple change of your index definition, which I'm realizing we didn't really talk about until now, and I find that quite impressive. Instead of needing to say that it's a vector field in this field, you just say, hey, this is where the content is. Please embed it with this model. Initially, it will be Voyage models, and we'll look to expand that. This is in private preview today, and we're definitely taking nominations. If you're interested in this feature, please find me after this talk, and I'd be happy to work with you. And then at query time, it's just a natural language user query. So no need to send something out to an external system. It'll all be done within the data plane. What this sort of amounts to between hybrid search and these data actions is this idea of greater seamlessness within MongoDB. We really do want all these features to kind of flow into the database, sort of a shift left towards the database, rather than be a set of disparate systems that you, the user, have to kind of keep in your head and manage, which at scale can be kind of an operational nightmare. Where this is going is providing more ways to use Voyage embedding models. So having dedicated inference APIs and auto-embedding, that will be very critical towards making embedding models additionally sort of disappear into the database. And then I'd be very remiss if I didn't mention that vector search and community is now available in public preview. Also for enterprise server, for those of you interested in that. And we have a whole refresh of our docs today talking about this. It was mentioned in the keynote. Heard a lot of applause for it, so I imagine some folks are jazzed. But yeah, it's a new deployment model for the same type of software, and it makes it much more accessible. But yeah, I would say fundamentally, we're really excited for what's coming. We're really excited for these types of workloads people are building and building a capability that can continue to support them. And yeah, without further ado, we have a quick fundamentals. If you want to learn just the basics before we hill climb up to these more advanced features, I would totally recommend checking out the skill badge. I think there's also like a MongoDB skill badge booth somewhere. I forget exactly where it is. And now I'm going to actually hand it over to Azim from Microsoft, who's going to be talking a little bit more about how Atlas can be made to work well within Microsoft and build AI apps easily and more securely. Thank you very much. Thanks.
Thank you, Henry, for the great content. Folks, like all of you, I'm super excited to learn about all these innovations in MongoDB Atlas to deliver the next generation of search and AI workloads. Now, to realize the full potential of all these innovations in MongoDB Atlas, you need a cloud provider such as Microsoft Azure, which is a leader in AI. The partnership between MongoDB and Microsoft spans over a decade, and through our engineering collaboration, MongoDB Atlas is now deeply integrated into Microsoft Intelligent Data Platform, thus enabling our customers to realize the full value of their unique data and realize the full power of cloud. In my section of the presentation, in the next couple of minutes, I'm going to talk about how MongoDB Atlas with its vector search capabilities and integration with Azure AI Foundry can help solve enterprise AI challenges. So let's share some context. As we tap into the power of Gen AI, it is important to realize that the technology brings a new set of risks. Some of them are pretty complex. One of the most common issues is known as hallucination, where a model generates inaccurate output even with a clear set of inputs. We also have to consider the prompt injection attacks and the jailbreaks, where someone intentionally tries to manipulate the model with malicious prompts, resulting unintended behavior. And there's the issue of a model generating harmful content or ungrounded output. So the point being here is that while the possibilities of Gen AI are exciting, understanding these risks and building ways to mitigate them is going to be key to success if we want to earn the trust of the users using them. At Microsoft, we tackle these challenges through what we call our Trustworthy AI framework, right? Which is a set of core principles: fairness, reliability and safety, privacy and security, inclusiveness, transparency and accountability. And we have translated these principles into real actionable commitments and tools so that you can build build enterprise AI from the ground up. That includes things like strong privacy assessment and consent management, data encryption and confidential computing to protect sensitive information. We also have got tools for groundedness detection so that the model generates the reliable response. So in summary, what we call is a defense in depth approach so that you can build AI systems ready from the ground up. So one of the Azure solutions that kind of implement this trustworthy AI framework is known as Azure AI Foundry, which is which brings together all the key components in one unified platform so that you can build and deploy AI agents and apps at scale, right? Foundry provides a broad model catalog, over 11,000 models to choose from Azure AI Foundry, not Azure, Azure OpenAI, as well as partner models such as Llama 2 and Mistral. Not only models, it provides you ability to customize and fine-tune your model to fit your specific needs. And then it provides knowledge integration capability, like ability to connect external resources such as MongoDB Atlas to ground your responses in real data. You can build intelligent multi-agent applications with just a few clicks with support for agent-to-agent, A2A, MCP, and frameworks like LangChain. Trust is super critical, so Foundry includes built-in content safety. And then through observability, you can basically evaluate your models in production and assess. So all of these you can use through the tools that you are already using today: Copilot Studio, Visual Studio, GitHub. And Foundry allows you to deploy your models in the cloud, on premises via Azure Arc, and locally via Foundry.local. We are going to touch on some of the Foundry features. As I talked about, this is just showing, as we speak at this point, Foundry provides you more than 11,000 plus models. And you name it, if you think of any other partners, we probably have a model to be used in Foundry. One of the key features of Foundry is Azure AI Content Safety, which plays a critical role in keeping your Gen AI applications safe and responsible. It's built to detect and filter harmful content across different types of input: text, images, and code. So I'm not going to go over all the different types of filters it provides. The point here is that Azure AI Content Safety is able to detect and filter both your inputs as well as the response from the model. So basically both layer of protection. So as I talked about Foundry evaluation. So one of the features of Foundry is that it can generate synthetic data. Many times you need to be able to assess your models with real data, but if you don't have your data in-house, you can use the synthetic data generation of Azure AI Foundry to evaluate your model. Now let's look at how all these come together to provide safety in real time. And by the way, I'm going to show some of these in the demo. It all starts with your application front end, where user provides a prompt to your application. On your application back end, the prompt gets combined with a system message and grounding data. So this grounding is the part where Azure Foundry and MongoDB Atlas integrates, because here Azure AI Foundry is doing a vector search from MongoDB Atlas to bring your data and ground the response in real data. So now that modified prompt gets passed to Azure AI Content Safety to check for harmful input, PII, or prompt injection attacks. If anything is flagged, it gets filtered or blocked. And then the modified prompt then gets passed to the model, which generates a response. Response then gets passed back through Azure AI Content Safety for groundedness check or harmful content, etc., etc. So this dual layer of protection, both for prompt and the response, basically provides you the trust and enables you to kind of safe, responsible AI. Now let's go into the demo to see how all these things play together. Let's build a Contoso camping product using MongoDB, Atlas, and Azure AI Foundry. We'll start with the model leaderboard. You can see more than 11,000 models. You can browse the model leaderboards and compare across different metrics such as quality, cost, and throughput. You can also do a custom comparison of models here and bring your metrics such as cost versus quality here. And once you are happy with your evaluation and comparison, you can go ahead and deploy the model here. For our case, we have selected GPT-4o for generation and text embedding 002 for actually embedding. And during the model deployment, you can also customize for token size and things. In the interest of time, I've got deployed for both of my models. Now let's go to the playground and test this model, GPT-4 model. At this point, I haven't added any data and it's not grounded in data. So if I run a query on Contoso camping, it interprets this as a fictional product, right? Because it's not grounded in data. Let's try to fix this. Go to MongoDB Atlas, and where I have my collection in products, in the content field, I have the product description, and my vector embedding is stored in the embedding field. So the first step to do is to create a vector search index. You go to search indexes, create an index, and you can see the definition here on the embedding field. Pretty simple. Once that is done, you go back to Foundry and create a vector index to connect to that index that I created in MongoDB Atlas. So I'm going to select MongoDB Atlas and create a pre-configured connection. And then I provide my database and collection name and the index name here. And for embedding, I'm going to use the ADA 002. Follow the rest of the steps, and then I'm going to use my pre-configured index already for the rest of the steps. With this vector index created in Azure AI Foundry, let's go back to Chat Playground. And I'm going to now add that index that I just created here. And then let's try my query again to see what happens, right? I expect to see the camping product data now being sent as the real data. You can see it has given me the price of the product, and through my citation link, I can verify that this data is grounded in MongoDB Atlas. Let's now try to run some off-topic query. Can I light a bonfire in Banff National Park? Since this model is only grounded in MongoDB Atlas data, this off-topic query response is not helpful. Let's try to fix this with a system message to guide the model with its role and how to respond politely to off-topic queries. So with the system message defined, if I run this query again, you can see the model now responds politely saying that, hey, this is not its role, with its role clearly defined and routing the customer to kind of Contoso camping site. Now, let's try to improve the model safety with Foundry safety messages. I'm going to use the filter for harmful content, ungrounded and copyright and jailbreak. And then I'm going to apply this thing, and then just for the sake of, and I apologize for the really offensive query, this is just to prove a point. Apologies for the offensive query, but if I run this query, you can see that it is not completely blocked. It is recognized, but not completely blocked. Same thing happens to a jailbreak query as well. It recognizes, but it doesn't block it. So to improve these safety features, we're going to use Foundry content filters. Every model in Azure AI Foundry comes with a default filter, but you can always customize these filters. In this particular case, I've defined 2 filters, one that blocks all of these violence, hate, sexual content, and harm. The other filter is a little bit more permissive. It blocks some of them. In the previous test that I was doing, I was using the more permissive filter. Now I'm going to use the stricter filter with here and run the same query. Here I'm going to use the more stricter filter and run the same offensive query here. But this time you can see the model blocks it with a clear hate message, right? It says that, it recognizes that, and your application can handle this accordingly. Same thing happens on the jailbreak attempt as well. It clearly blocks it and marks this as a jailbreak attempt. So this approach increases the security while allowing flexibility. So I'm going to wrap up with the Foundry evaluation. You can evaluate your Foundry models through industry standard metrics or based on your own data. In my case, I have evaluated my model based on my MongoDB product data. This shows strong fluency, low similarity, and then strong safety. So with this kind of concludes my demo. In summary, MongoDB Atlas integration with Azure AI Foundry can help solve, help accelerate development of your enterprise AI capability. So thank you all with this, and please feel free to stop at our booth at Microsoft if you have any further questions on the content that I provided. Thank you.